Welcome to Ready to Drive. In this video, we're going to be doing an optimization practice problem relating to time. This is kind of fun one, a common one you'll find in textbooks, but here we are. We have a river. We'd like to get from the point A to P. The river is 3 kilometers wide. P is 8 kilometers down the way from A. And we can either row or run, or a combination of the both. And we run at different speed from which we row. And the question is, can we find a point C along the river that if we row from A to C and then run from C to P, we minimize the time it takes to get from A to P? So I know that's pretty exciting stuff, so we'll get into that shortly. I'm going to first do a quick review of the four-step strategy for solving optimization problems. If you like a little more detail, please check out my first video on optimization, which I will link in the description below. But without further ado, let's begin. So here's a brief review of the optimization strategy. Step one is to define the function that is to be optimized and make sure it's expressed in terms of one variable only. So you may have to do a little maneuvering if you have sort of what appears to be two independent variables to express one of those in terms of the other, so that there's only one independent variable in the function. Step two is to find the critical values of the function by setting the first derivative equal to 0. Step three is to consider the domain of the function, and then that will sort of help you to establish the location of the absolute max or min. Now, there's kind of two scenarios. If the endpoints matter, so if you have a closed interval, then you would want to use the candidates test. And in the case where they don't matter, and that's quite often when there's maybe also when there's just one critical value and you just have to establish if it's the absolute max or min, then in that case you can use the second derivative test. And step four is to state the conclusion in the context of the problem. So here's our practice problem. You're about to launch a boat at point A on one side of a river, and you would like to get to a point P on the other side of the river. So here's the picture. Here's the river. Here are the points A and P. And A is the river is 3 kilometers across, and you'd like to get to point P, which is 8 kilometers along the river on the opposite side. So here's the scenario. You can row directly to P at a rate of 6 kilometers per hour, or you could row to some point on the other side of the river before P. So let's see, you could go to a point like here, row to that point there, and then run the rest of the way along the embankment. And so obviously you can row at 6 kilometers per hour. Of course, we're assuming that there's like no current and that it doesn't matter what angle you row at, not very realistic. And you can run at a rate of 8 kilometers per hour. So the question is, at what point should you land your boat on the other side of the river in order to minimize the time it takes to get from A to P? And now no one's ruled out the possibility that no one's ruled out that way. Maybe it's just fastest to row right across and then run to P, or perhaps it is just better to row directly. So you could go this way and run all the way along, or you could go to just row all the time and not actually do any running from A to P. Or we're curious if there's a position that would sort of minimize the time it takes. Okay, so here is our diagram and the facts that we row at 6 kilometers per hour and run at 8 kilometers per hour, so we don't forget that. So the first step is to define the function that has to be optimized, which in this case is time. We'd like to minimize time. And if we think about the formula relating distance, rate, and time, d equals RT, we would like to solve for time. So time is distance over rate. But of course, our rate varies depending whether we're in the water or rowing or running. So we need to introduce a variable to figure these out. So let's call that point opposite A, B, and the point that we would like to optimize, the point on land that we'd like to get to before we start running, if we ever start running, we'll call that C. And we need a variable, an independent variable. So C is the thing that's varying. It could be anywhere from B all the way to P. So let's call the distance between B and C x, and that will mean that CP will be 8 minus x. And then what we have to do is think about the time for each part of this journey. So let's think about rowing from A to C. If we row from A to C, then we know we can say that our time in the water will just be distance rowed, which is AC, divided by the rate, which is 6. And if you see here, you have a little right triangle, ABC, and we can do the Pythagorean theorem and get that the length AC is x squared plus 9, square root, sorry. So square root of x squared plus 9 over 6, that is a formula for time spent in water. Now, once we get to C and we run across over, land, we have the distance we will run is CP, and our rate is 8. And we just established that CP is 8 minus x over 8. And so our total time for the trip will be the sum of those two quantities, as given here. So step 2 of the process is to find the critical value or values of our function, which is our time function. So before we find the derivative, it might make sense to sort of get it ready to easily take the derivative of. So I'm going to rewrite that radical as x squared plus 9 to the half. I'm going to, I could write that, I could divide through by that 8, or I could just write it as 1/8 8 minus x, whichever way, or you could just write this as 1 minus 1/8 x, whatever works. So the derivative would be, so we have the 1/6. If we look at x squared plus 9 to the half, by the chain rule, by the power rule, we'll have half x squared plus 9 to the minus half times, by the chain rule, the derivative of the inside function, which is 2x. And then we have plus 1/8, because that's a constant. We can ignore that for a moment. And the derivative of 8 minus x is just -1. So if we tidy that up, we get, let's see, 1/12. Well, this 2 cancels with that 2. I'm going to just rewrite it back in radical form because it's a little tidier that way. So we're going to get 1x over 6 times the square root of x squared plus 9. And then we have this minus 1/8 here, and we're going to set that derivative to be 0 to find the critical values. So let's bring the 1/8 to the other side. So we have x squared plus 9 equals 1/8. And then we can kind of cross multiply, I guess. We could get 8x equals 6 times the square root of x squared plus 9. And we could actually, let's see, reduce this. So we can do 2 into 8 is 4, and 2 into 6 is 3. And then the best thing to do to get rid of that radical would be to square both sides. So if we square both sides, we will get 16x squared equals 3 squared is 9. The radical goes away, so we have this, x squared plus 9. And then we would get, let's see, bring it up here, 16x squared equals 9x squared plus 81. 7x squared equals 81, or x equals the square root of 81 over 7. And so that's that, and we could turn that into a decimal just for simplicity. So it appears that 3.4 kilometers down the river from A will give us the minimum time. So you should be asking yourself, well, how do we know that 3.4 kilometers down the river will in fact be the minimal time? Okay, so it's very easy to just, once you get a critical value, just assume that's the answer, but you must remember to consider the domain and do a test to check for the exact location of the absolute minimum. So if we think about, let's see, remember this distance was x, and this was 8 minus x. So it is possible that, so the domain, what are the possible values of x? Let me just use white here. So so the domain is, well, it is possible that we row directly to B, in that which case x would be 0. So x could be 0, and it could be as much as, well, what if we don't even bother running and we just row directly from A to P? So it could be as much as 8. So once we've established this domain, and so 0, the endpoint 0 and 8 are indeed candidates, what we have to do is test our value. So remember our critical value, we got that x equals 3.4 is the critical value. So we need to make ourselves this little table. We're going to do the candidates test where we consider the endpoints and we also consider any critical values, and we basically plug those values into our time function. So if you plug in 0 for x, you would get 1.5 here. If you plug in 8 for x, you would get that it takes you 1.42 hours. And if you plug 3.4 in, it gives you 1.33 hours. So in fact, this is the minimum time value on that interval. So with confidence, you can make your conclusion, which is that you should row your boat to a point 3.4 kilometers down the river. So that point C is 3.4 kilometers from B, and then run the rest of the way in order to minimize your travel time. Thank you for sticking around to the very end of the video. If you enjoyed it, found it useful, please do like the video and subscribe to my channel, Ready to Derive, and check out some of my other videos.